about the old method, no problem. Still now nice. Okay. First question is the pressure in an automobile tire depends on. You read the question. There is an automobile tire. Depends on the temperature of air in the tire. When the air temperature is 25 degrees Celsius, the pressure gives 210 kilopascal. If the volume of the tire is 0.025 meter cube, determine the pressure rise in the tire when the air temperature in the tire rises to 50 degrees Celsius. That means there is a one tire here, right? One tire. This is state 1. So they tell you its pressure P1 is 210 kilopascal in gauge, they say gauge. And temperature is 25 degrees Celsius, means 25 times 273, 298 Kelvin. And they also say the volume of the tire, right? The volume of the tire 0.025 meter cube. So pressure, temperature and volume, I know. No problem, right? So now they say that the air temperature is heated from initial to final, some number. So temperature T2 becomes 50 degrees Celsius, that means 50 plus 273 Kelvin. Right? And they tell you what is the rise in pressure. Delta P, how much? Delta P becomes P2 minus P1. If you can calculate P2, then you are able to calculate delta P. So P1 I know, right? So remember, this is gauge pressure is given. So you have to convert absolute pressure plus 100, because in this question it is written atmospheric pressure 100 kilopascal. So 100 kilopascal, then I can write 310 kilopascal. This is the absolute pressure. Okay, so do you remember I tell you, you can use P1 V1 by T1, P2 V2 by T2. Remember, right? In the class I tell you. So constant volume process, that means this volume also 0.025 meter cube. That means I can say V1 and V2 are same, right? Constant volume process. Then you can see I can neglect V1 and V2. So now I am going to substitute the data. So what is P1? 310 kilopascal. What is temperature T1? Is 298 Kelvin. What is P2? I am going to find out. And what is T2? T2 is 50 times plus 273. What is the number? 323. So what is the value of P2? 323 times 298 by 310. Then I get my answer. I get my answer here. 336 kilopascal. Alright, done. So what is the rising pressure? So rising pressure delta P. Rising pressure delta P is equivalent to P2 minus P1. So what is P2? 336, 310. And the answer is 26 kilopascal. Alright, so now we see our work. Okay. Number question B. Question B, they tell you B. Okay, determine the amount of air that must be bled off. They tell you, now I remove some air. When it reaches 50 degrees Celsius, I remove some air from that system. Right? I remove this air. So what happens? Pressure drops. But temperature is same according to the question. What happens? Pressure drops to initial pressure 310 kPa. So now you can see now screen is coming, right? Now I am going to put lecture console notebook. This is notebook, right? Notebook. This way. The reason is, you know, they work this station for a long time. 3 hours around there. They work here. Because it is heated up. Okay. So now you can see we are lucky at least. So you get 336. So this one you understand already. So rising pressure is 26 kilopascal. I know. So now, secondly, what happens? What happens? Secondly, I release some air from the tire. Then temperature is 50 degrees Celsius. But pressure drops to 310. Right, what I did here actually, okay, I explained here. So PV diagram, right? You can see initially there is a temperature T1. Correct, initial temperature is T1, which is 298 Kelvin. What is the initial pressure? 310. This is V1, this is P1. So, at constant volume process, this is T2, I have to find. This is 50 degrees Celsius. So, it goes from state 1 to state 2 at constant volume process, right? Correct. Now, what I do? Now, I release the pressure. That means the pressure decreases from 1 to 2. With this temperature. When I release the pressure, what happens? At that point, I can calculate the mass. M1 or initial I, P1 V1 by RT1. I can calculate the mass, right? So at that point, I release some mass. I release some mass. Some mass is released. Some mass is released. So what happens? Pressure decreases to initial pressure P1, which is equal to 310 kilopascal. Right? But temperature is maintained same. But this one is T3, another position line. T2 is here, okay. 50 degrees Celsius. So, what is the amount of mass of air at that position? This one becomes, pressure is 310, temperature is 50 degree, right? 323, and what is R? 0.287 for air. Then T, PV, right? This is V, not P. This is V. This is V2, right? And this one should be 323. So this value is equivalent to 1. This value is equivalent to Why? Tell me. You understand this or not? This volume is equivalent to the tire volume, not the air volume. This is the tire volume. In the question, tire creates the volume. The volume is fixed. Not air volume, tire volume. Right? For example, this is ideal gas. What is the concept? Remember, the ideal gas, the molecules are, occupied a lot of space. Even though you release some air from the system to surrounding, the volume is really the same. Because the molecules are moving, right? They occupy the whole volume. Understand? That's why the volume is fixed. So what I can do here? Initial mass I can calculate. Pi Vi by RT. So this is Pi. Vi is fixed. This one. Because of the volume of air, fixed volume. It doesn't change. It's a tire volume, right? Because the molecule occupy the whole tires. That's why this volume is fixed. It doesn't change. Even though you release air from the system. So that's why they are fixed. So Tf is given same as 50 degrees. And this is the initial temperature. I can calculate the mass. I can calculate the mass. And these indicate 0.287. 0.287 is 8.3145 divided by 29. Air molecular mass is 29. Then you can get 0.27 kilojoule per kilogram Kelvin. Unit is kilogram per kilojoule per kilogram Kelvin, right? So how much air is released from the system? Delta M, right? Mf minus. This is the amount of mass should be released from the system. Mi is this value, Mf is this value. This amount of air is released. Okay? This is the ideal gas concept. Any question? No question. That means you understand, right? Or do not understand. It means I hope you understand because this concept is not new. Okay? And second question is important for this. This one. Try to understand. A piston cylinder device as shown in figure 2 contains air at 200 kilopascal. This one contains air at 200 kilopascal. That means initial temperature pressure is 200 kilopascal with the initial temperature of 303 Kelvin. That means I can write T1 is 200 kilopascal. Temperature T1 is 303 Kelvin. All right. Then what happens here? Take a look. Then initial volume I can write 400 liter. And 400 liter should be converted to meter cube. Okay, remember I give you the formula. V1 becomes 0.4 liter cube. That means 1000 liter is equivalent to 1 meter cube. You should know this. Okay, secondly, the system is now brought in thermal contact with the heat source of Q. That means some heat source is applied to the system. The mass of the piston is so heavy. Take a look. If two concepts I teach you, today also I teach you this one. This piston is heavy, right? So initial pressure is 200 kilopascal. Is not enough to move the piston, right? When you apply heat, the pressure and temperature is building up initially. Then when the pressure becomes some number, right, 400 kilopascal, then the piston moves. Okay, when the pressure becomes 400, this guy moves to state 2 to state 3, and they tell you the final volume is double. The state 3, when it reach here, the volume becomes double to V1, right? That's all. And the question is, you have to calculate the final temperature. At that point, what is the temperature? What is the temperature when the piston starts to move? That means at that point, what is the temperature? Draw PV and TV diagrams to show how the system changes from initial state to final state. Understand? So now, state 1 is I know, right? Fine. So state 1 I know. So what is the state 2? State 2 and state 1 are nearly the same position. Doesn't move, right? Yeah. Because of constant volume. So I can write V2 is equivalent to V1 is equivalent to 0.4 meter cube. I can write, no problem. So can I write this equation? I am going to calculate the intermediate temperature. I am going to calculate this first. Right. So I can write P1 by T1, P2 by T2. So V1 and V2 are same. I can cancel them. No problem. Okay. So what is the value of T1? Any idea?
T1 303 Kelvin.
What is the P1? Is given 200 kilopascal. What is T1? 303.
P1. I thought T1. Sorry.
Temperature of 303. So what is the P2? P2?
400.
400.
400. Yeah.
Yes. When the pressure becomes 400, then it moves.
Yeah.
Before that, it never moves. So that's why P2 is 400. That means I can write P2 here is 400. At that point, pressure is 400. So I can write, what is P1? P1 is 200. T1 is 303. You just write P2 is 400. T2 I do not know. Then I can calculate T2. T2 is equivalent to 606. Very good. Right. So now I apply heat. The piston tends to move and it goes to state 3. Right? It goes to state 3. At state 3, what is V3? Double of initial volume, right? 0.8 meter cube. What is P3? P3 is 400 kilopascal. Done. So now you can write P2 V2 by T2 is equivalent to P3 V3 by T2. You can write. So what I can write now? Tell me. I can write P1 V1 by T1. P2 V2 by T2. P3 V3 by T3. Done. Right. Then I can write both ways. Now I am going to find T3. This one I am going to find. Then I choose P2. What is the value of P2? Tell me, P2 is 400. V2? 0.4. T2? 606. P3? What is P3? 400. Same concentrate. Then V3 0.8. T3 I do not know. Right? So T3 becomes 1, 2, 1, 2. Very simple. Then this one cancel. So this one and this one is 2. Done. Very simple. Right? Remember P1 V1 by T1, the same system, closed system. I can write P1 V1 by T1, P2 V2 by T2, P3 V3 by T2. My question is why I can write. Why? You understand why I write this? Show you. So what is the total? What is the basic equation? Tell me. Basic equation PV equals to MRT. And becomes
Your favorite transport.
PV by
Everyday fall.
RT. Alright. Then can I write this way? Because this is the same system, same mass. Mass is fixed. So can I write this way? And becomes P1 V1 by RT1, P2 V2 by RT2, P3 RT2. And from here I can write, right? Same thing, right? Then I can write P1 V1 by T1, P2 V2 by T2, P3 V3 by T3. R, cancel. Understand how I write this? This is the way. I'm going later. Don't worry.
Sir, sorry, so the answer for A is 606, is it?
Yes.
Not 1212. Because it's the final.
No. This is final. This is A.
This is A.
This is
Then
A.
606 is
6066 B. Now you have to draw the PV and TV diagram. Take a look. This is PV diagram. T1. This is for T2. This is for T3, right? I can write T1, T2, T3. So what is state 1? This is V1, this is P1, this is state 1. So 1 to 2 it goes by constant temp volume process. Constant volume process, right? 1 to 2. And 2 to 3 is constant pressure process. Understand? That means P1, this is P2 and P3 are same, right? So V1 and V2 are same. Then I can write V1 and V2 are same, and here P2 and P3 are same. This is PV diagram. If you want to draw the process on TV diagram, this is T, P. Then you have to put the constant pressure line. This is P1. I can draw. This is P2. Then what is the state 1? P1, T1, and V1. Initially is constant volume process. That's why it goes from 1 to 2. This is 2. Here you can get P2. And 2 to 3 it follows constant pressure process up to here. This is 3. This is P3. this one V1 and V2 are same. Then from there you can calculate P. Understand?
Yes.
Very simple. So I go to the previous slide, and after that I twist something on the same question. You get it? Okay. Okay, now I twist this question. Can I? You need some time, okay? To wait for another 2 minutes. Okay, take a look. Now I put the stopper here, right? You remember? Now I put the stopper here. Okay? I change. I do some twisting. I plan to put the stopper. Alright, but here there is no stopper. No. No stopper. So in that question they tell you a piston cylinder device as shown in this figure. Initial pressure is 200 kilopascal, temperature 3003, volume is 0.4 meter cube. The system is now brought in thermal contact. The mass of the piston, no. I remove this line. In that case, this is not heavy piston, right? Okay. Apply heat. The piston is moving from here to here. Correct. And volume becomes double. And further heating up, the final pressure is 400. Okay, kilopascal. Now you have to do the same thing. Understand? In that case, this is the final pressure, right? The final pressure is, in that case, you can write down the question, right? Final pressure is, final volume is double, and the final pressure is 400. Okay. So now they tell you calculate the final temperature, calculate the intermediate temperature here. Okay. So initial is here, state 1. So state 2 becomes, this indicates state 1.
I think those are.
When the piston goes here, it becomes state 2. And what is the state 3? Yes, very good. Then what is the initial pressure? Right. Initial pressure is 200 kilopascal. Initial temperature is 303 Kelvin. And volume, initial volume is given, right? 0.4 meter cube. So at state 2, what is P2? P2 also 200. Constant pressure process. And V2, 0.8 meter cube. Double. Then what is T2? T2 is the intermediate temperature. This one. Then T1, V1 by T1. P2 by T2. So P1, P2 cancel. So V1 is 0.4, T1 is 303, 0.8, T2. (606 Kelvin). So this is the intermediate temperature. What is the temperature when the piston? No, not this. When the piston touch the stopper. When the piston touch the stopper, right? When the piston touch. Stop. Okay. So how do you calculate the final temperature? Easy, right? So P2 V2 by T2 equivalent to P3 V3 by T3. Then you can calculate. Then you can calculate. Can I go next page?
Yes.
Next page. This one. Touch. So I can write T3 by T3. V2 by T2. T2 I know, right? So V3 and V2 are cancelled, constant volume. So what is P3? 400, right? 400. What is T3? I do not know. What is P2? 200. T2? 306. So T3? Same answer, right? But drawing is different. What is the PV diagram? What is PV diagram? This is P1. What is P1? This is P1. This is V1. So 1 to 2 constant pressure vices. So I can say 1 to 2 is it? Constant. This is 1. This is 2.
And then go one more. Next 3.
And then one more.
Going up.
This is T3. V is going up. Oh, very good. You understand?
Of course.
It's like this.
Best student.
Okay, I twist the question and you can see it's different. Constant pressure process, then constant volume. The previous one, constant volume, then pressure. Now I change. Alright, so I can go to the next page. This question. This question and previous one is nearly the same. Take a look. A piston cylinder device as shown in this figure 3 contains liquid vapor at 200 kilopascal with the quality of 70%. At this stage, the piston is resting on a pair of stops and enclosed the volume is 400 liter or 0.1 meter cube. The system is now brought in thermal contact with the heat source of Q. The mass of the piston is so heavy that 400 kilopascal pressure is required to move it. The system is heated until the volume is dropped. Calculate the initial mass of water vapor mixture and volumes of liquid phase and gaseous phase B. calculate the final temperature
Yes,
and
you go,
volume,
I will.
draw PV and TV diagrams and show how the system changes from initial to final. So this one, I do not think is difficult.
Shy.
Alright. How to calculate? What is state 1?
Must run. The,
State 1, what is the temperature?
I mean, the game must run.
What is the pressure? 200 kilopascal. Take a look, don't understand first. Temperature, I do not know. Pressure is this one. And what is another information? Another information is quality is given, right? Then you can calculate V1. Then total volume I know. Then I can calculate the mass. And which I discussed today in the class. Alright. So state 1 is, I write for you. State 1, I go to the previous slide. So this one indicates state 1, initial. When you apply heat, it doesn't move. When the pressure becomes 400 kilopascal, then this guy moves. Then finally it goes to here. Same as previous question. So what is P1? P1 is 200 kilopascal. P2 at that point, P2 is 400 kilopascal. And what is P3? Also 400 kilopascal. Because 1 to 2 is a constant volume process. Constant volume process. And 2 to 3 is constant pressure process. Okay? This is the understanding. And here they give me the pressure and the quality, some number, right? 70%. Then I can find the initial volume. They also give me the total volume. 400 liter. That means 0.4 meter cube. Then I can calculate the total mass. Okay? May I go to next slide?
Go.
Okay. State 1. What is the state 1? 200. With the quality of 0.7. Then I know VA. This one. VG. This one. So what is the initial temperature? T1. What is the T1? Tell me. T1 is 120.1, right? Alright. Now you have to calculate what? V1. VA plus X times Vg minus Va. You substitute all the value, then you can find 0.6204 meter cube kilogram. Right. So what is the total volume? Tell me. Total volume at state 1? 400 liter. 0.4 meter cube. So what is the total mass? V1 by specific volume. 0.4 divided by 0.6204. And I get here 0.645. So how you can calculate the liquid mass and vapor mass? I give you 2 star, right? How to find vapor mass? Quality times total mass. You know this, right? Mass of liquid phase 1 minus X times total mass. So mg I get here according to this question, this equation, I can find mg. Mg is equivalent to 0.4515 kilogram, and mf I get 0.1935. In the question, they also tell you find the volumes of liquid phase and the gaseous phase. What is the volume of liquid phase? Volume of liquid phase is VF, right? This one is defined by MF times specific volume VF. Specific volume VF is this value. What is MF? 0.1935 times 0.001061. Then you can get 2.053 10 power minus 4.
0.1933.
Alright, 35. You have to multiply, okay? Then Vg mg times Vg. Mg is, I get here 0.4515 and V 0.88578. I get the answer 0.3999, right? Roughly 0.4 meters cube. What is the meaning of it? Right? Total volume, right? Vg. 0.3999 is answer. This is the basic. Okay, so now what we can see? I can calculate the volume of liquid phase and volume of gaseous phase. Volume of gaseous phase is much higher than that of liquid phase. Very clear. So now calculate the final temperature and volume. How to know? You remember the question first time? Put on a stopper. When the pressure becomes 400, right? Then it goes to, moving up. And final volume is double of the initial volume. Okay. So here, what is the final pressure? This one, right? So what is the V3? I know. V3 I know, right?
Yeah.
So my question is, so what is the location of V2? What is the position of V2? This is important.
Same as V2.
What is the final pressure? P2 is
V2 is 400.
400. Oh, I can follow you. Okay, P2. I can write 400 kilopascal. Then what is the V2? Final volume is what is final volume? Tell me. V2 is same, right? V1 and V2 are same. Yes? V1 and V2 are same.
Yes.
No, 0.62. 0.6204 meter cube kilogram. Okay. So at 400, take a look. At 400, where is the 400? This is 400, right? At 400, what is the Vg? Can you see this? What I write? Correct, this one. And what is V2? So which one is higher? V2 is higher, right? Yes. So V2 is higher than, what you can write? I can write here, right? Because V2 is higher than Vg at 400 kilopascal. So what is the nature of the state? Superheated vapor. Very good.
Very good.
This is superheated vapor. So answer is solved. So they tell me what is the final temperature. So final state is 3, I tell you, right? 1 to 2 constant volume, 2 to 3 constant pressure. So what is the P3? I can write for you. Final state. Final state is 3. At 3, we get P3, which is 400 kilopascal. And what is the V3? Double of initial volume, right? That means 2 times 0.6204. That means I get 1.2408 meter cube kilogram. Alright? So what we can understand? We understand that V3 also, right? We understand from here V3 also higher than Vg at 400 kilopascal. So the state is superheated vapor, right? Superheated vapor phase. Now how you can calculate the temperature? So what is the nature of the state? State 3 tells me state 3 has 400 kilopascal and specific volume 1.2408 meter cube per kilogram. Now I have to go table A6, right? Because superheated vapor with respect to this kilopascal and this specific volume. Then I can calculate final temperature. Understand? Alright? Then you go to superheated table. Superheated table tells me this indicates 400 kilopascal, right? 0.4 megapascal. And what is the specific volume?
1.24.
1.2408. Where is the location of 1.2408? 1 point somewhere here, right?
800 degree to 900 degree.
Right? Then I can write this is the final temperature T3. Then I can write T3 minus 800, 900 minus 800 is equivalent to, what is the specific volume? At T3 is 1.2408, at 800 1.23, 1.23730, at 900 1.35, 298, 1.23730, and finally I get T3 803.02 degree. All right. This is the answer. This is the final temperature. Not easy. You have to work hard. Okay.
So you need to make the previous slide.
Sorry.
Your previous slide.
Previous slide.
Yeah.
Subscribe to Nico.
This is the problem. No? Wow. How to go previous slide?
Too fast.
Okay, this one. This one, right? Next one. Okay. Have you taken all? Now you have to draw PV and TV diagram. PV diagram. PV diagram. Alright, then this is state 1, then from 1 to 2, constant volume process, then 2 to 3, constant pressure. So this one, if you draw this line, this one is T3, T2, sorry, B1 and B2 are same. Alright, if you are drawing PV diagram, PV diagram, then this is T1. Okay, at state 1 is here, right? 1. Then this one is T2. And this one state 1. It goes from 1 to 2. Constant volume process. Right? And later it follows. This is T2. P1, B1 and B2 are same. Three, right? Constant pressure. And temperature is higher, right? This is temperature T3. Okay, this is the way you have to draw. This one, 1 to 2 constant volume process, 2 to 3 constant pressure process. Alright, and this indicates temperature T2, this line indicates temperature T1, and this indicates temperature T2. Similarly, on TV diagram, P1, this one P2, this point T2, T1, and T3, right? State 1, state 2, state 3.